Okay, here is a one-dimensional kinematics problem that involves free fall. And we are going to figure out here a guy named Simon Dumont, one of the original snowboarders who did, quarter pipe, half pipe, big jumps, big airs. He, quite a long time ago, I forget, early 2000s, did this jump at Sunday River in Maine. He jumped on a quarter pipe. So a quarter pipe is a ramp that's like this. That's the quarter of a pipe. And he jumped that in on a snowboard. And he went flying up into the air and came back down. And the height he went, that height was 10.4 meters. It was actually 34 feet is what they measured it in. I'll try to attach a video of that. You can Google it on YouTube, Simon Dumont quarter pipe, and watch it. So what we're trying to find out today is how much time, how long was Simon in the air? So how much time? So I'm going to draw a better picture here, a motion diagram. He leaves the edge of the pipe going pretty fast, so we got big spaces. And then, of course, due to gravity, he is going to slow down and then get to some peak. And then on the way down, he will speed up, right? So here he's going down, there he's going up. Now, if we ignore the effects of air resistance, which we do a lot here because it makes things simpler at first, we know some things about that, in that this motion, whatever this velocity was here, this velocity initial at that instant, it's going to be the same size. This velocity final will be the same size. And that's true at every place where it's the same level, same altitude, it's going to have equal speeds, opposite directions. Some other things we know about this is that at this top, this velocity in the y direction at the top well, that equals 0, because that's where you're turning around. He was going up, slowed down, had to turn around, got to hit 0 as you do that. So that is, at that instant, 0 velocity in the y direction. We also know some things about this kind of motion, is that since it's the same level, that this change in time going up is the same time interval for going down. And that's of a lot of value here for this problem. Because with the equations we have, we can solve intervals from one place to another, but we can't solve for the time to go all the way around. So say we do the whole interval, the whole thing. We've got a velocity initial, which we don't know. We've got a velocity at the end, which we know is negative, the velocity initial, but we don't know it. Y initial, we can call that 0, and Y final is also 0. We don't know the time. And we don't know, we do know the acceleration in the y direction is 9.8 meters per second squared. It is directed downward always downward, so we're making that negative. So too many things I don't know. Actually, I don't know 3 things. I need to know everything but 2 here in order to solve that. So now I got to pick a different interval where I know more stuff. And the interval where I know a lot of stuff is from the very bottom to the top, because I know this speed at the top, that velocity at the top. So just the up part. Or you could do just the down. Both of those, you know one of the velocities. I'm going to do the up. So that initial velocity is unknown to me. The final velocity of just the up part, that's 0. Because at the highest point, you have to hit 0. If you're not, you're still going up. And once you start going down, it's now, you have a velocity downward. I'm going to call y initial here 0. Call the edge of that's 0. Y final, that's up there. That's the 10.4 meters high. 10.4 meters. That is up from the 0. So I'm indicating where is that relative to my 0? That's above the 0. So that means that's got to be a plus, a positive number. I'm taking positive numbers, positive to be upward, negative to be downward. The time frame, we still don't know. And the acceleration in free fall is that negative 9.8 meters per second squared. And again, that's negative because it's down. Keep track of your directions. Direction is one of the reasons a lot of people get these things wrong, is they don't account for the direction correctly. Okay, so what do I want here, though? I don't need the velocity at the beginning. I mean, I could go find that out and figure it out later. But if I find this time, that's essentially half of the time in the air. So if I find that time up is equal to the time down. Time up and time down are equal. So I'm going to find that time up and then double it. So I want to find that time. I don't know that initial, so I'm not going to use that. I'm going to use the equation without initial velocity, and that equation is y final equals y initial plus vy final t minus 1/2 ay t squared. Delta t, really. Delta t. Okay, some of you might not have that equation. That is one of the kinematics equation that you can use. You can derive that from the velocity time graph for uniform accelerated motion. And it's essentially, if you know the final velocity, you subtract the accelerated motion from as if it was moving constantly at that final velocity. All right, so let's plug in our numbers. Let's see what we got. Y final is 10.4. Y initial is 0. Velocity final is 0. Whoop. That's a plus right there. Times the time. That's nice. That's going to cancel out. Minus 1/2 negative 9.8 time squared. All right. So I get 10.4 is going to equal, there's a negative, that becomes a positive, 4.9 t squared. Do a little math there. And we're going to get that t squared is equal to 10.4 divided by 4.9. Enter. Take the square root of that. We got 1.45 seconds. 1.46 seconds. That's how much time it took him to get to the top only. So in air, 2 times that delta time up. So that is 2 times 1.46, which equals, I'm going to use the whole thing, times 2. We get 2.91 seconds in the air. 2.91 seconds. So that's how you find hang time if you know the height that something's jumped or gone upwards. Good luck.